Hi Year 12, welcome to a series of 4 videos for the topic of mathematical induction. In this first lesson we're going to look at proof. So I'm going to cover what is proof and the different types of proof, and then I'll finish off with an introduction to the process of mathematical induction. Now proof is one of the main things that distinguishes mathematics from the sciences. Scientists conduct experiments and they suggest a theory, but this is called a conjecture in mathematics. And then mathematicians, we use proof to prove conjectures and then make them into theorems. Now, arguably one of the most famous theorems is Fermat's last theorem. And for many years it was called Fermat's conjecture, nearly 400 years, and it states that no 3 positive integers can be found, a, b, and c, that will satisfy this equation a to the power of n plus b to the power of n equals c to the power of n if n is greater than 2. So this should look familiar to you. It's like Pythagoras' theorem. And if this is a squared plus b squared plus is equal to c squared, we know that there are lots of positive integers that will satisfy that equation. They're called Pythagorean triads. But Fermat said that it's never going to work if those powers are greater than 2. And this was unproven for so many years until this gentleman, Andrew Wiles, who's an English mathematician, he proved it in 1995. And since then it's been known as Fermat's last theorem. And of course not every conjecture has been proven. And here's another famous one, Goldback's conjecture. And he proposed that every even integer greater than 2 is the sum of 2 prime numbers. And this one is as yet unproven. And so are many of the Millennium Prize problems by the Clay Institute. If you've read about these, it's very interesting. It's a set of 7 problems that if you solve one of them, they are worth $1 million. And so far, only one of them has been solved. Now let's have a look at the language of proof. A conjecture is something that all evidence suggests is true. But a theorem is a statement which has a proof and it is interesting for its own sake. A lemma is a statement that has a proof, but it's not interesting for its own sake. It is often used in the proof of something else. A corollary is something else that can be proved after we've proved a theorem. And an axiom is a statement that's accepted as true that cannot be proven. Now there are 2 types of proof. There's direct proof and there's indirect proof. And in Extension 1 Maths, we're only going to be interested in direct proof. If you want to know more about indirect proof, then you have to look at the Extension 2 syllabus. Now, a mathematical proof is a correct argument which establishes the truth of a mathematical statement. And regardless of the type of proof that you're trying to construct, we have a basic setting out of a proof that we follow. It's going to start with a statement that we want to prove, which is the conjecture. Then it has a sequence of logical mathematical statements with justification if required, and it makes use of facts like axioms or theorems that we already know in order to produce new facts. And then it's going to finish with a conclusion. Let's look at a geometric proof. Now I know geometry is no longer part of the Advanced or Extension 1 syllabus, but it is required knowledge. And you have covered this in years 9 and 10. And the thing with geometric proof is it's a really good example of how we set out a proof logically. So let's prove that the diagonals are equal in a rectangle. We're going to start by drawing a diagram. So basically what I want to prove is that AC is equal to BD. And so I'm going to start by writing a required to prove statement, RTP. I want to prove that AC is equal to BD. And we need to do this through congruent triangles. So I need to find 3 facts to prove that those 2 triangles are congruent, triangle ADC and triangle BCD. Now here's the thing, we can use any fact about a rectangle to prove that those 2 triangles are congruent, except that diagonals are equal. So we can't use the thing we're trying to prove in the proof. That's like a circular argument. But we've got plenty of information. We'll start with DC is a common side to both triangles. We also know that AD is equal to BC because opposite sides in a rectangle are equal. And finally, angle D is equal to angle C, which is 90 degrees. So therefore, triangle ADC is congruent to triangle BCD. Reason, right angle hypotenuse side. Now once we have congruent triangles, we know that this side here must equal this side here. So therefore, AC is equal to BD. Reason, corresponding sides in congruent triangles are equal. Therefore, the diagonals are equal in a rectangle. We also have trigonometric proof, where we have to prove that two expressions are equal. It's quite different to geometric proof, but again, you should be quite familiar with this. This is part of the course, and you should have been doing questions like this in Year 11. Prove that 1 plus sine 2 alpha all over 1 plus cos 2 alpha is equal to a half, and then in brackets 1 plus tan alpha all squared. So remember, we're going to start with the left-hand side and work through in a series of logical steps until we reach the right-hand side. So our left-hand side is 1 plus sine 2 alpha all over 1 plus cos 2 alpha. Now I know that sine 2 alpha is 2 sine alpha cos alpha, but there are a couple of different forms of cos 2 alpha, so we need to think carefully about which one we want. Have a look here. I know that tan alpha is sine alpha over cos alpha, so that's suggesting to me we want to keep cos on the denominator. So here's my substitutions. 1 plus 2 sine alpha cos alpha, 1 plus 2 cos squared alpha, take away 1. And you'll notice how I don't give any reasons or justifications for those substitutions. So that's a real difference between trigonometric proof and geometric proof. All right, let's tidy up that denominator. Now I'm going to bring the half out and split that into two fractions like this. So I've brought this half out the front. I've got 1 over cos squared alpha plus 2 sine alpha cos alpha over cos squared alpha. Now 1 on cos squared alpha is sec squared alpha, and I can cancel one of the cos's out of here. That's going to give me 2 sine alpha over cos alpha, which is 2 tan alpha. And there it is. And we have one last step to go. Have a look where we're going. 1 plus tan alpha all squared, sec squared alpha plus 2 tan alpha. We need to change this. Now there's a Pythagorean identity. Sec squared alpha is equal to 1 plus tan squared alpha. So let's make that substitution. And now tan squared alpha plus 2 tan alpha plus 1 factorized is 1 plus tan alpha all squared. So it's equal to the right-hand side. And so it is proven. And of course we can prove theorems like the remainder theorem. If a polynomial p of x is divided by x minus a, then the remainder is p of a. Here's the proof. Let's let p of x equal x minus a, because we're dividing it by x minus a, multiplied by q of x, another polynomial, plus a remainder. Now when we substitute in x is equal to a, this is what we get. A take away a, which is 0, which wipes this out. And so p of a is actually equal to the remainder. And so we've proven it. Now there are many types of direct proof which can be applied to different fields in mathematics, and we've just looked at a couple of them. But one particular type is called mathematical induction. Now mathematical induction is often used for proofs involving infinity. And here's an example. Prove for all numbers n that are elements of the set of positive integers, so all positive integers n, that 1 plus 4 plus 7 plus ... plus 3n take away 2 is equal to n on 2 outside of 3n take away 1. And we're going to have a look at this question at the beginning of our next lesson. Now this is how mathematical induction works. Suppose there is an infinite staircase and you're asked to prove that all of the steps are painted green. Well, the only way that you could do that would be to check each step one by one. But suppose that the steps have been painted according to this rule. If a step is painted green, then the next step is also painted green. Now how many steps do you need to check? Well, hopefully you're telling me just one, just the first one. Because if the first one's painted green, then the second one must be painted green. And if the second one's painted green, then the third one must be painted green, etc., etc. And that's the process of mathematical induction. We start by showing the statement is true for some initial or base value. It's often n equals 1, but not always. Then we assume it's true for some arbitrary value of n, so n equals k. Then we have to prove that it's true for the next value, n equals k plus 1. And then, since it is true for n equals 1, and then proven true for n equals 1 plus 1 equals 2, and so on. Therefore, it is true for all n. Okay, that's it for this lesson. In our next lesson, we're going to look further at mathematical induction, and in particular, the series type questions.